So good morning everyone. So in last lecture we have seen fused deposition modeling, that is FDM machine. So basically we have started with the rapid prototyping processes. So in that we are going to learn five types of rapid prototyping process. First one was the fused deposition modeling, that is FDM we called as in short name. Second one is the SLS, selective laser sintering, and third one is the SLA, stereolithography, and uh, fourth one is what, LOM, LOM, that is laminated object manufacturing, and fifth one we are going to see the
Hello, sir. Hello, sir.
SGS.
Sir, we cannot.
Overhead. How?
So, twin heads
Cannot.
moved in X and Y direction. The table in which building is done, the table moves in Z direction. Slicing you can see. So this parameter inputs thickness, road width, and this is already decided by the system only. The software only it will be decided. Okay. Then machine uses a separate head for each material. Appropriate head is loaded. Nozzle of required diameter is set. So these are the steps which you have to, before actual manufacturing, you have to decide. Hmm? So what type of material you have to use, head material, everything. This all you have to think. And even you have to upload the material, means you have to fill the spool appropriate model and support materials are loaded. Means you have to load the material, support material as well as the main material you have to load on the machine. Okay. So in modern machines, there will be a pair of cartridge intelligent spools for model and support, and they can switch automatically. So in latest machines, it is not required. So you have to load and everything. Though it will show the message that the spool is empty, and it will take the material automatically. So no user has to insert the wire and purge it. Okay. So in latest machines that facility is available, and even in latest machine this layer thickness, road widths, and the number of layers for the base are also decided by the software. Or you can there is option automatically select. There is option, if you do manually you can decide the layer thickness, and according to that your nozzle should be there. Okay. Then set the temperature on the both chambers and working volume. It is 270 degrees for the model, comma 265 degree for support, and 70 degree for working volume. See here, huh? So means 270 degrees for the model, and for support it is this much, and then working volume it is 70 degrees. So allow time so has to reach the those stable condition. This is what, due to temperature difference is here, 270 degree model and working volume is 70 degrees, there will be the heat transfer will occurs, and that again the semi liquid material will go to the solid form. Hmm? Uh, so some time is required, although sometimes so as to reach those to stable condition. So this occurs like here. The reason is there. The chamber temperature ensure that respective material is heated with the exact overheat, and more temperature will cause more penetration into the substrate and remelting occurs. So we have to maintain them because first layer we have pasted, so we have to maintain the temperature every time, because if we pour more heated material on the first layer will also get melted. So less temperature will cause the poor flow and addition with this substrate. So we have to maintain the exact temperature of support material as well as working volume and melting temperature, everything. So the temperature in working volume ensures that the substrate is at the required conditions. Hmm? So Of late, those also get set automatically by reading the barcode on the spools. Okay, so there is a temperature when you take that spools. There a temperature is given at what temperature the material will get uh, can be operated. So temperatures are given according to that code. We have to input the values. Hmm? So this is how the first hard foam is mounted on the table and the pores to see that the both nozzles are in good conditions. So first what we do for 2-3 layers we pour the material that hard foam earlier material we will paste it and we have to check that it is working in good condition or not. Huh? And then the smooth purging indicate that parameters are correct. After that the smooth purging will be there. So the it will check that the parameters are correct or not and then material is within its shelf life. Okay, of late instead of foam perfect sheet is also used. So I don't think this perfect sheet is now been used because directly I am seeing that 2-3 layers of material have been poured and we have to see that it is pasting it is right or not or it's there is some problem. So according to by visually we can see, so we can stop that and again if any problem we can change the inputs. Okay, so then jog to bring the nozzle to touch to just touch the foam surface and start the process. See here this is important. uh, there's in earlier process they are pasting the hard foam and then soft foam, so we have to bring the nozzle to exactly to it and then we have to start the processing. So the first layer of the support is deposited to create the base of the material, base of the build. So as I said you, at the start, what we will do, we will put the support material layer, and then we will start with the actual material. Okay. So the model material is deposited. The material deposited is in the form of ribbon or rectangular cross section or a slice thickness of X road width. So here that material is deposited and the material deposited is in the form of ribbon of rectangular cross section. And the first contour is made followed by an area filling inside a zigzag manner. The angle of zigzag pattern can be set or it can be randomized. So earlier, so randomizing will improve the homogeneity of the prototype. Okay. So the model material is pasted in a zigzag pattern. Some angle is set it, so according to that we have to paste it. So it will maintain the homogeneity of the prototype. Okay. And moreover, whenever support is required, the support heads deposits the material there. Okay, so before when we transfer the actual 3D model in STL format to the system, it identifies the support areas where the support material should be deposited. The software will identify and according to the coding, so it will instruct the machine to deposit the support material and main material as I already said you. So this is the same thing. And then one thing is that once in a while the nozzle goes and rubs on the brush to clean itself. So this is called purging. Okay, so the nozzle goes and rubs on the brush to clean itself. Okay, some material will be there and the nozzle tip, so it will be cleaned. So that process called purging. Okay, so after building, take out the foam along with the part and support. See, the supports are removed carefully. This will be fairly easy exact expect for interior feature since the support material has a poor addition with the model material. So this is very important. The support material should have the poor addition with the model material. If it has more addition, it will not get removed. So this is very important. So it is weak due to the coarse deposition. See, so if we do the fine deposition of the material of support material, so it will have more addition. So it will not weak, it will strong then. So important is that the coarse deposition should be there. So that it will, the grains coarse deposition means if the paste will have the size of the grains inside the paste will be uh, of a higher diameter, that is coarse deposition we can say. So so due to that higher size, so it will get, the strength will be weak, like that. And then it has a different color. How to identify if model material and support material are of same color? uh, Identification will be the problem. So that's why the different material should be of different color. Okay. And they, this is important note, they have also introduced the water soluble support material. So the support material should be water soluble, means once we take that build our part from 3D machine, we will put in a water solution, that is acetone solution mostly we put, and here water soluble means it acetone and water will be there, so we will put in that, so the support material will get soluble inside that, and the main product we can take it out from that. Okay, the part is finished and painted as required. Okay, so support material we can remove, that process is not mentioned in this slide. I can say that process is called fletching process we called it. Hmm? Fletching process, through fletching process is a, there is one separate instrument device instrument is there, inside that the solution is there, benzene acetone solution is there, inside that we will put this part, and once we put this part, our fdm part inside that, uh, so once we put that part, that support material will get separated. So that process is called fletching also. Okay. And see, there are advantages of FDM. Any thermoplastic material can be used as long as appropriate head is available. Okay, and the parts are very strong. So any thermoplastic material can be used over here for FDM machine, and it does not employ lasers, so no lasers are used. So it is very safe. So this FDM process is very safe as no lasers are used, and it does not use liquid and powder raw materials, hence clean. It can be kept in an office environment as a 3D printer. Okay, very easy to remove the support. This is probably the easiest of all RP process. So support, removing the support material in the FDM machine is very easy, and this is the cheapest machine. Okay, and due to their business policy, the cost of RP are of all RP are comparables. Okay, so these are the advantages. So any thermoplastic material can be used, and no lasers, that is good one, and easy to remove the support. And then this according to the market value, the this is the cheapest machine. So this is also one advantage as cost wise we can say. The limitations are, as every point of volume is addressed by the mechanical device, it is very slow. So the main problem is what? The time. Okay, so for printing the part, the time required is more. Okay, as mechanical devices are used over here. And not very accurate compared to SLA. And I will say why SLA is good and SGC is good. Uh, okay, later I will show, when we will see the slides of that, we will compare with FDM. And not isotropic means that material is not material property is not same at each point. Okay. Then this is one machine specification is there. It is developed by Stratasys USA, and this is how the machine is defined. You can see, so marketed by India, and all raw material used spool of diameter, and raw material any thermoplastic is possible, ABS plastic in colors, polycarbonate, polyamide, wax you can use. Okay, and maximum built in all of this is that plate area. This is that plate area. You can say 60 mm length and 500 mm width and 600 mm diameter. Okay, so this is how the built area is, maximum built envelope we can build on that machine. So extrusion head is there, type of head is the extrusion head, the tool you can say, and the minimum layer thickness is 0.127 mm. Okay, so these are the various parts built through FDM machine. You can see the sample FDM parts. This is another model. This is a FDM machine where the material is, primary material is a wax. Hmm? Wax, and they are popular for jewelry manufacture. So layer is machined to maintain the thickness accurately. Okay. Sweeps. It's a sweeps. It's a company name, has 5 such machines. And this sweeps is nothing but it is the industry is in Andheri only. Andheri sweeps. One company is there, sweeps. So it alone has 5 such machines for jewelry manufacturing. And the machine details are over given here. So this is the latest machine in FDM only. You can see here multi jet modeling is there. Means more than, we have seen 2 jets. One was the for support material, one for the build material. So here multi nozzles are there. We can use multi nozzles. Hence it is very fast. So multi nozzles are used. So earlier we have seen only 2. Here we can see multi nozzles. So due to this multi nozzles, the machine is very fast, and quick verification of concepts are there. So this is a platform built, and this is a building material over here. You can see, and supply is again here the wire form, and this is X and Y, and this plate is moving in minus Z. It will go downside. So this is a latest machine in FDM only, multi-jet modeling. So here was a single jet, and here this is a basic diagram. And this is a multi-jet modeling. The next process is selective laser sintering. Selective laser sintering. Okay. So from the name itself, you can understand that here we will use laser, right, to solidify the material. Huh? So laser will be used over here. So this technique was developed by University of Texas, Austin, and marketed by the various companies of America, Germany. Okay. So important is that the raw material is the powder. The raw material we used here is in powder form. Okay. Earlier in FDM, we have seen the raw material was in wired form. Here the raw material is in powder form. Okay, the principle is similar to powder metallurgy, but for the absence of compaction. Okay, so green part is prepared on RP machines after partial sintering, and sintering is completed inside another furnace. Okay, so just as SLA, here also the laser light is used. When it is scanned on the selected region over the layer of powder, the particles of that region fuses together, and remaining powder acts as a support, as in case of LOM. laminated object manufacture. Okay. Laser beam is positioned using a small mirror capable of deflecting two directions. Therefore, this has a very low inertia and high speed and accuracy. The power of laser decides the layer thickness. See, here the thickness of the layer is controlled by the laser. The power of laser decides the layer thickness. This is a very important point. Huh? Okay. Then explicit support structures are not required. Means external different dedicated support structures are not required. The powder will remaining powder will automatically act as a support for this. Wide variety of powders can be used. Okay, this is important. Wide varieties of powder can be used. Just see this diagram. 5 minutes. Observe this diagram. Okay, let's follow from laser. Okay, here you can see CO2 laser is used. Okay, the type of laser is CO2. Okay, here optics are there. Optics are there for deflecting the laser. Okay, so increasing the intensity, controlling the laser, the optics is there. Then scanning mirror is there, so the optics will control the laser and it will be passed through a scanning mirrors and it will reflect to the surface. Okay, this much part is clear. Okay. Here you can see two powder cartridges there. Powder cartridge 1, powder cartridge 2. Okay, here what happens, this will, from here the roller is there, powder leveling roller is there. As this part goes down, the powder material will be spreaded on this. As this part goes down, the powder material will be spreaded on this, and this through this roller the extra powder will be waved out to this part. It will collect the remaining powder material. Okay, this part will go downwards. Here the part cylinder and powder bed, this will go downwards, and the extra powder will be pushed to this feeding or collecting system. Okay, and then once this process completed, through this laser beam which has been controlled by the system, it will pass through this material or part cylinder, and as laser beam falls on the powder material and it gets solidified, and the fusion occurs over here and the part will be solidified. So, and again for next layer, again this cylinder, the powder bed will go down, this will go in -z, and again the excess material will be taken away through the powder leveling roller. From here the roller will come and the extra powder will be passed to here collecting system. So again the laser will be, through lasers we will solidify the part, and like that the layer by layer, and here a powder will be there in this chamber, so that will act as a support for this system. So the steps are: slicing is done, the working volume is maintained with appropriate temperature so that laser supplies the energy required to cross the threshold sintering temperatures. Okay, and the inert environment is created using the continuous supply of gas such as nitrogen. So here the inert gas is supplied, nitrogen is supplied to maintain the uh, environment. Okay, so this is to minimize the fire hazards as the fine particles have high activation. Okay, each slice or layer is realized using the following steps: the table lowers by the layer thickness. Okay, this we have to set. The table lowers by the layer thickness. And the layer of the powder is spread and leveled using the contra rotating roller. The beam scans the layer of powder and thus required region is selectively centered. Okay. After all layers are made, the table rises completely, revealing the block of cake with the part inside. Okay. So once the part is built, that whole table will rise up, and from that the powder will be there. The block of cake it's saying like that, and from that we have to take out the part inside from it. Okay. Surrounding powder is soft and it is removed using a suitable brush. Through brush we can remove that the powder around the part, and this powder is reusable. Again, that powder can be reused. So the part is kept in a suitable hot chamber to complete the sintering. So once getting the part from that bed, we have to put it in a hot chamber so that it gets a sintering is a heat treatment process like. So just we have to heat it for some time, so that the part will get hardened. Then the metallic prototypes require copper impregnation in another furnace to improve their polishability. If you want to improve the uh, polishability of that material, you have to some copper impregnation is required. Okay, the part is finished and painted as required. So this is a selective laser sintering machine. These are some machine details of that. This is again one more machine of EOS, and this is the comparison of those both the machines. It is not required for us because the latest machines are now available. Then advantage of this process is a wide variety of powders can be used. As I said, thermoplastic powders you can use. Wide variety of powders can be used. The fast due to tiny moving mirror parts as in SLA, and metallic parts can be made. This was the first commercial successfully metal RP process. Okay, so selective laser sintering, you can make metal parts also. Hmm? Suitable for making a injection molding tools. So injection molding tools you can make through this SLA process. So only limitation is surface finish is less detected by the particle size. Okay, so here if you take a fine particle, means fine powder, the surface finish will be improved, I think, because surface finish is less detected by the particle size. Some while fusing, the particle size will be bonded, and at the upper, that the last layer, you will see the particles fusing, and there some part they will be outside. So this is similar. Bring out the similarities between laminated object manufacturing and SLS. Hmm. So the built outcome is a block or a cylinder. Remaining material is a support, and laser power to be matched with the layer thickness. So these are the similarities between LOM and SLS. LOM, I think in last lecture we have seen LOM, and there also we put the laminas and we cut through the laser. And similarities between SLA and SLS. So the laser used for polymerization and sintering. Laser scanning is same as galvanometer based. Okay? And laser power to be matched with the layer thickness. So today we have seen two process. One was the FDM, another is a SLS.